Welcome to this lecture series in real analysis. In this lecture, we will be discussing the intermediate value theorem, which is a very interesting and very useful theorem in real analysis. And all we need to know very well is the epsilon delta criterion of continuity to fully follow this lecture. Okay, so with that, let us move on. Here are some problems for practice. And now let us get started. So what we are going to do is first look at a certain property about intervals, or rather a defining property of intervals, which I have labeled as, this small t-shirt statement that convex sets are intervals. Okay, so what am I saying? Fix some subset J of R, J is non-empty, such that whenever 2 points in J are chosen, one less than the other, then the entire closed interval that you can form using those 2 points is contained in J. So pictorially, if suppose whenever I choose a point A and a point B and both are in J, then the entire thing sandwiched between them is contained in J. So then J is an interval. And recall what are intervals? We defined intervals. Intervals are sets of this sort, semi-open or, both open, semi-open, and both closed. You can also have these kinds of intervals. All of these were intervals. So recall what were intervals. So what we are saying is that everything which is convex, this is the convexity property, that whenever you choose 2 points, everything between them is also there. That's convexity. So here we are saying that convex sets are intervals. The converse is obvious. So intervals are precisely the convex subsets of the reals. Okay, that's what this lemma is saying, and the proof is very simple. It's just, I will not write much. So what we do is we choose P as the infimum of J and Q as the supremum of J. And then you can show that, so here is the exercise. Show that J is one of these 4 things. So either it is this thing, or this thing, or that thing, or that thing. Okay. So I'll leave this as an exercise, and with that, let us now state and prove the intermediate value property, which I'm sure you have seen somewhere in your life before. Alright, so what we are given is a continuous function on a closed interval such that f takes opposite signs on A and B. This is just a fancy way of saying that whatever is the sign of fa, meaning if fa is negative, then fb is positive, and if fa is positive, then fb is negative. That's what this is saying. Then there is some element c strictly between a and b, such that f of c is 0. Visually, what does this theorem become? Suppose fa is negative and fb is positive, then the theorem is saying that somewhere between a and b, the function must take the value 0. In other words, of course we are assuming continuity of the function, because without that this is certainly not true. So in more colloquial terms, suppose I were to draw the graph of the function starting at this point and ending here, then since I cannot lift my pen, thanks to continuity of the function, I cannot lift my pen, and therefore it should be intuitively clear that at some point I will pass through the x-axis, and I will therefore pass through a point with this property that the value of the function there is 0. And there may be multiple such points. We are not saying anything about the uniqueness of such points, but they do definitely exist, is what we are saying. Okay. So let's try to prove it now, and we will assume that fa is less than 0 and fb is greater than 0. The other case is that fa is greater than 0 and fb is less than 0, but that is very, very similar to this one. So this is the only thing we will look at the proof for. Okay, and just for my sanity, I will draw something here. Okay, so these are the function values. So this is the value at a and that is the value at b. All right. And the main idea of the proof is the following. The value of the function at a is negative, and therefore by continuity of the function, by continuity of the function will stay negative in a neighborhood of a. If fa is negative, the function stays negative for some time. Just use the epsilon delta criterion. Suppose, just for the sake of understanding, suppose this were -1, and you draw an epsilon band about this point. Choose epsilon very small, let's say even half or something, 1/3, half, whatever. Then by the epsilon delta criterion, there is a delta neighborhood around the point A, such that whenever we pick a point in this delta neighborhood, which is also in the domain of the function value is, or the corresponding point in the graph is in this epsilon band, and therefore the function value is between the points -1 plus epsilon and -1 minus epsilon, both of which are negative numbers. Okay, so geometrically, you make a small epsilon band and make a small neighborhood around the point A. If your neighborhood is small enough, the graph of the function corresponding to that neighborhood or above that neighborhood will be in this epsilon band and hence will stay negative. The function will stay negative for some time. So that is one thing that we know. And then what we will do is we will define, or we will collect all those points x in this interval such that the function is negative through and through that, entirely through that part. Okay, so here is the main definition. So define S as those points in the interval such that f of y is less than 0. I'm sorry, what am I writing? Yeah, f of y is less than 0 for all points y in a comma x. Right, that is the definition of the set S. So again, what are we saying? A point x is in this set S if whenever we choose a point between a and x, including a and x, what we see is that the value of the function there is negative. Now it is clear that a lies in S. A lies in S simply because f of a is negative. But by what we explained, here the continuity of the function says that something greater than a must also lie in the set S, because the function stays negative in an entire interval or an entire neighborhood around a. Okay, so if we take the point x0 as the supremum of S, then here is another most important observation. If we take any x in this region, or in other words, I can just write this interval is contained in S. So you take x0 as the supremum of S, and x0 is strictly greater than a. So x0 is strictly greater than a, simply because there is an entire neighborhood about the point A such that the function takes negative value everywhere there. So all of these points are in the set S, and therefore if you take the supremum of S, you will get something strictly greater than a. So that's that. And why is this true? Well, x0 is the supremum of S, And we are saying that everything less than x naught and at least a is there in S. So if we choose something less than x naught, if it is not in S, what does that mean? It means that the function takes positive values somewhere before or at that point. But then there is no question of S containing any point in this region, right? So let me enlarge this and explain. X naught is here. We are saying that everything before x naught is there in the set S. Suppose not, then there is something here which is not in S. Call this maybe C. Suppose C is not in S. That means either f of C is positive or f of some point before C is positive. In either case, none of these points can be in S. None of these points can be in S, because if any were in S, then that would mean that everything before it had negative value of f. But that is contradicted. So this is something that I have justified verbally, but I hope you're able to write a formal proof of it. Okay, so we have that, and now there are three cases. So case one is that f of x naught is negative. Case 2, f of x naught is 0. And case 3, f of x naught is positive. Now I should have also said before I came here, the supremum of S is strictly less than B. So let me write that. Because if x naught were equal to B, then the function would take positive value in a neighborhood around x naught, and that would contradict this part. Since f takes positive value at B, it takes positive value in an entire neighborhood around B, and hence no point there can lie here, and that would contradict this deduction. So x naught is strictly less than B. You could have justified that immediately. Okay, yeah, all right. So now this is first case, that f of x naught is less than 0. So x naught is somewhere here, let's say, and the value there is less than 0. But then again, by continuity of the function will take negative values in an entire neighborhood around the point x naught. And now note that a point bigger than x naught is also in S, because the function is taking negative values everywhere before x naught. It is taking negative values everywhere in a neighborhood of x naught. So there is something greater than x naught such that the function takes negative values everywhere before it, in fact including it. So that point will be in S, and that point is greater than x naught, contradicting the fact that x naught is supremum of S. Okay, so this case is not possible. Second case is favorable. This is what we wanted. We wanted a point strictly between A and B where the function takes 0 value. So if that is the case, then we are fine. And case 3 is also something we will rule out, because suppose x naught is here and the value of the function is positive here, then the value will be positive in an entire neighborhood around the point x naught, and therefore any point on the left side of x naught and also in this neighborhood, the function will take positive value. Let me draw that again. X naught is here, the function takes positive value at x naught. So there is an entire neighborhood where the function takes only positive values, and if we choose a point in this region towards the left of x naught, we will see that that point cannot be in S, because the function takes positive value there. So that point is not in S, and that contradicts this deduction. So this case is also ruled out. So that's it. So we must have that case 2 holds, and that proves the intermediate value theorem. So I did not write the proof, but I hope I have been able to explain it sufficiently well for you to be able to write it yourself. And now let us finish this lecture with a little bit of a generalization of this theorem. So here I is an interval, and we have a continuous function from the interval to reals, then this thing is also an interval. So the image of an interval under a continuous function is again an interval, perhaps of different type. So if you start with an interval of this sort, you may not end up getting the same sort of interval, meaning this is an interval where both the endpoints are open. If you take the image of it under a continuous function, you may not get a both open interval. You may get one-sided closed interval or something, or both-sided closed. Okay, but it will be an interval though. Why is that? The reason is convexity property. So the reason is that f of I is convex. Again, what does that mean? It means that whenever you choose 2 points in f of I, one less than the other, then everything between them will also be there in f of I. And the reason for that is the intermediate value property that we just proved. So suppose I choose 2 points in f of I. Let's call them x and y. Since x is in f of I, x is equal to f of a for some point a. The figure is going to be horrible. Yeah, this will have to do. So choose 2 points x and y in f of I. We want to show that this entire closed interval is there in f of I. Now, let's say x is f of a and y is f of b. We want to show that everything here is also there in the image, but by the intermediate value theorem, f must take every value in between, right? If f takes the value x and it takes the value I, by the intermediate value theorem, it must take every value in between. This is not how we stated the intermediate value theorem. We said that if f of x is negative and f of y is positive, then f must take the value 0, which is same as saying that 0 is a point between x and y, so it should take the value 0, but you could have said that for anything between x and y, not just the point 0. So the intermediate value theorem is really saying that if f takes 2 values, then it takes all the values in between. That's what the intermediate value theorem is saying. And therefore, f of I is convex and convex sets are intervals, and we have proven this. So in this lecture, I did not write a lot of things, but I'm sure you were able to figure things out by yourself or write them by yourself. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.